Hello, and I hope you're as excited as I am to talk about my research topic, magnetic Skyrmions in chiral multilayers. This project is hosted by the University of Leeds and funded by the EPSRC and Kinetic. First of all, what is a Skamion? A Skamion is essentially a topologically supported magnetic vortex. We'll explain more on what that means in a minute. We have two types. We have a Nail-type Skamion, shown in figure A, and a block-type Skamion, shown in figure B. In thin films, these are encouraged to form by the Jalaszynski-Maria interaction, shown in the equation below. D is simply a tensor, and S represents our electron spins, spin I and spin J. The origins of the Jalaszynski-Maria interaction come from the weak ferromagnetism that you can find in antiferromagnetic materials. This posed quite a problem for the theoreticians of condensed matter physics before the 1960s. Why are they stable? When the DMI is present, it is a result of crystal symmetry. Maria, in his paper, outlines a number of rules which indicate the direction of the D tensor. Furthermore, you also have a degree of topological protection. In the equation shown, we have a quantized winding number. What this means is that you cannot smoothly deform between one state and another, a state of uniform magnetization and a state with a skyrmionic vortex in it. This lends it a degree of energetic stability. Now, this is interesting from a fundamental science perspective, but we'd like to use these for real applications. Unfortunately, it turns out to be quite difficult to manipulate Skyrmions using standard electric and magnetic fields. This is where the idea of a spin torque comes in. Now, it is proposed that in 4 and 5D transition metals, so platinum, palladium, tungsten, rhodium, and others, you have hopping probabilities of your electrons in the s and d orbitals, which are greater than the hopping probabilities of a d to d orbital hop. Now, if you could remember back to basic chemistry, the difference between the s and the d orbital is the orbital angular momentum. Because of conservation of angular momentum, this manifests itself as a generalized torque, which lets us have a spin polarized current, which can then be injected into another layer. Now, rhodium is a D-type transition metal, so why would we be interested in adding iron to it? Normally, the spin polarization of an injected spin current is perpendicular to the direction of charge current and the direction of spin current flow. This is unfortunate because it causes problems when trying to manipulate magnetic structures in perpendicular magnetic anisotropy samples, meaning in thin films where you have the magnetic spins pointing out of the plane of the material. Fortunately, this effect not only exists in transition metals, but it also exists in their compounds. And it turns out that when you have lower symmetry compounds, you can modify the direction of spin polarization so that it's no longer perfectly perpendicular to the direction of charge current and the direction of spin injected current. This proves much more useful for manipulating Skyrmions in thin films. From this, we have a number of potential applications. Data transfer and data storage is an obvious one. The presence of a Skyrmion and the absence of it can represent a 1 and a 0 respectively. Skyrmions are deterministic. You can quite easily move them, you can create them, and you can destroy them. Skyrmions can also be made into a very, very small size, which proves very beneficial when you're looking at the problems that the hard drive industry is facing at the moment, with difficulties reducing the size of magnetic domains and yet being able to still keep them stable and efficiently manipulate them. Skamions can be made a size of 10 nanometers, which is remarkably efficient if you're looking at it from an information density storage perspective. Further to that, we also have an interesting look at Skyrmion-based electronics and Skyrmion-based logic gates. computational studies have demonstrated that you can have Skamions doing logical operations much in the same way as you would on any other kind of logic gate. And, as a bonus, this also ties in very nicely with our other application, which is neuromorphic type computing with artificial synapses, and also probabilistic style computing. All of these combined make Scamions a very, very exciting platform for the development of computing as a whole, more generally. It has the potential to provide a really very unified field of expansion for the field, which would certainly prove very, very interesting given the limitations that transistor size, hard drive storage density, and other such things are running into at the moment. It's entirely different as well, the way that we'll think about electrical circuits when we can incorporate these probabilistic computing and artificial synapse elements into them. I hope this talk has proved very interesting, and I look forward to hearing any of your questions or comments. Thank you very much.